All right, Precalc 12b. We're back and we're going to be talking today a little bit this idea called continuity. So something being continuous is probably not a new concept, but when we bring limits into the conversation, we can kind of double up this idea of limits and kind of layer it with continuity to be able to say things a lot more precisely about whether something is continuous or not. So, just talk about what I have down there. Many physical systems are described as continuous unbroken functions. So if I were to say how far have I gone down the road? Well, at any point in time, I have gone, there's a continuous function that kind of says, hey, you're as time goes on and you're walking down the road, you're here, then here, then here, then here, then here, and there are no jumps or weird changes that go on. Even if I speed up or slow down, it's just going to change the way that everything's connected a little bit differently, but it's still all connected. It would be a continuous function. The little image that I have underneath of that, I worked for a couple summers in a laser spectroscopy lab during my undergrad degree. And when we are looking at the wavelength of different photons that are emitted during electrons changing or going between different energy levels, it's really neat because it's quantized. What that means is that the amount of energy given off is A or B, but not between A or B. That's a really oversimplified way to put it, but if you, for instance, had the simplest example ever, and there was option A was that you could give off, I'm just, without getting into units, give off 3 energy, or you could give off at B, jumping from, so let's say B to A is 3 energy, and then C to A would be 5 energy. If there were no other energy levels present, then you can't have 4. You can't have 4.5. You can't have 3.2. You either have 3 or 5. As such, you get these discrete values that if you're kind of like mapping whether that can be stated as a continuous system or not, well, that's probably not the case. You're going to have broken functions. Now, this thing down here, because of noise that happens in an actual lab, it looks actually like it's really continuous. But what is actually true is that these little individual lines here are peaks that denote, hey, there were photons at this energy level. And then it kind of falls back down to nothing, but there's this kind of background noise, and it doesn't get all the way back down to 0 in the short time while you're scanning through things. So then it peaks again, It's kind of interesting. But again, just there are certain reasons why you might be interested in looking at functions that are not continuous. And specifically when you start getting into certain theorems in calculus and before, you may have the requirement that what you're looking at is a continuous function. So knowing whether it's continuous or not is going to be important. So we are going to, as I just said, basically be able to pick out when things are continuous, when they're not, and as such, be able to apply certain theorems appropriately. So let's get right to it. And so the way that I usually try to describe to people what a continuous function is I gotta actually get my pencil to pick up here. It is when you have something that can be drawn without lifting your pencil or pen. So that little, I don't even know what you want to call it, the little curve that I just drew there, that is something that I drew without lifting my pen or pencil. If I do something like this, which is probably a little more familiar, other than the little arrows there at the end, that would be also something that I could do without lifting my pencil or pen, linear function. I could do that without lifting my pencil or pen. And so if it kind of passes the preliminary thing of not having to lift your pencil or pen, you're probably looking at a continuous function. Now, if we want to talk specifically about whether a function is continuous at a particular point, we can get a lot more technical because of the tools that we now have. So we are going to use limits. So what we're going to say is that in order for a function to be continuous at a point, it has to look like it's going there, and it has to actually be there. Now that we've seen some limit examples, we know that looking like it's going to be there is different from actually being there. For instance, if I have this nice little function and it looks like it's going to be here, and oh, I actually have a hole, and then on the other side I have this function that goes like this instead, we know that you can take the limit coming in from the left-hand side, you can take the limit coming in from the right-hand side. In this case, it would be two separate numbers. You can probably see that this is obviously a function that is not continuous. So we're going to say that one of the rules for continuity is that the limit has to exist. And if I take a look, I'm going to actually be able to highlight on here. I haven't been doing that, but if I take a look at this little piece right here, that's an important bit of the puzzle, because that is actually two separate statements all written into one. Because for the overall limit to exist, which is the limit as x approaches c at f of x, that implies that the limit as x approaches c from the right of f of x is equal to the limit as x approaches c from the left of f of x. So the left-handed and the right-handed limits have to be equal to each other, the one-sided limits. But the second part of that puzzle, this thing right here, is saying that we also need the function to exist in at that value of c, but not just exist. It has to agree with the limits that you've already determined. So we have this little function here, and it looks like it's going towards, if I say that this is at a y value of 3, looks like it's going to go towards 3. This part of here looks like it's going to go towards 3. And if we look at the actual value there, it's at a 3. The way that we'd be able to describe that is if this was g of x, for instance, we could say the limit, and I have to make an x value here. I'm going to say that the x value is actually 2. So the limit as x approaches 2 from the left of g of x is equal to 3. And the limit as x approaches 2 from the right of g of x is also equal to 3. So the left-handed and the right-hand limits are equal to each other, which means we can state that the overall limit is also equal to 3. That's important if we look down there, because the first highlighted bit that I have says that the overall limit as we approach this value of c, in this case it's the x value of 2, has to be equal to the actual function. So there's this bit is my first hint that things are going well, because if there is no overall limit, you're done. It doesn't agree from the left and the right, it is not going to be continuous. But if it meets that, and I also can put a 2 actually into the original function, no limits, you're looking at the actual point at x is equal to 2. Well, there's a point here, and it's at a value of 3, so that's equal to 3. And I'm going to write it out a little bit differently, but basically the way that it's written there, well, it's not f. Therefore, g of x is continuous at x is equal to 2. So this little series of 3 dots, that is a mathematical symbol that once we start getting into proofs a little more as you go forward, it gets used more so than you might have seen in the past. It is basically a switch for the word therefore, or it's a symbol for the word therefore. So in this case, because of what we've shown, which is the one-sided limit from the left is equal to the one-sided limit from the right, which means the overall limit exists, and the function exists at that same value, then because those two things are true, therefore, that triple little pyramid of dots there, g of x is continuous at a value of x is equal to 2. So we have shown that it's continuous. Now, this is for what's known as an interior point. So you might have noticed that earlier when you're looking at this thing. Wow, I'm really good at this game. So the interior point idea is basically this isn't always important because for functions that have domains of all real numbers, everything's an interior point. But sometimes, if you want to get a little bit fancier, you can have a function that only exists between two finite x values. So it might only exist between, for instance, x is equal to 0 and x is equal to 3 or something like that. So if that's true, then you loosen up the continuity requirements at the endpoints. Obviously, it's never going to be true that the function is going to be continuous according to the interior point definition when you get to an endpoint. If you were at this endpoint right here, you can't get ever a one-sided limit from the right-hand side on that right endpoint. There's just no function out there to exist. So it seems kind of weird that you have this nice connected function that looks like you could draw it with a pencil, but then you're going to say it's discontinuous at its ends. So we don't do that. We hold it to a little bit of a different standard when we look at an endpoint. So if you read the endpoint definition below, the idea is that it's continuous at a left endpoint if coming in from the right, it's going to be equal to the actual value. And it's continuous at a right endpoint if coming in from the left, it's going to be equal to the same value as the function. So instead of being an overall limit that is required to be equal to, it's equal to the one-sided limit that comes in from the side that exists. So in this particular case right here, if we come in at that left endpoint from the right, and it looks like it's going to get to a value of whatever the y value is, and it does actually get to that value, then we'll say that it's continuous. So this is basically our definition of continuity. Now, as you can probably tell, you would not want to do this for an infinite number of points. So most functions that we're interested in have a domain that in the real number system has an infinite number of values. Now, there are exceptions to that, of course, but there are pretty much everything that you've looked at up to this point are going to meet that requirement. So we don't want to have to do that everywhere. So we need to think of a smart way to deal with continuity when it's at something that's a little more obvious. And we'll get to that in a moment. So if a function is not continuous at a point C, then we say that the function is discontinuous at C, or that it has a point of discontinuity or a discontinuity at C. So that's just some terminology language-wise. So discontinuous at C, the function is, or there is a discontinuity or a point of discontinuity at C, depending on whether it is a point or not. Sometimes there's different reasons for things to be discontinuous. One of them is a point of discontinuity, but you could even just, maybe the more general thing to say here would actually be to say that it is a discontinuity. All right, so types of discontinuities. I'm going to come down here and say removable. So removable discontinuity is kind of what it sounds like. You've been clicking along, and here's the other part of the function, and you've removed something in the middle. So it is a point of discontinuity. It's a removable discontinuity, where all of a sudden it's just kind of like, oh, it's missing. And so that's what removable means. A jump discontinuity also is kind of what it sounds like. So you were coming along here, and then all of a sudden you jump down to a different value from where you were. So as you can probably imagine, a lot of these are going to be paired up with the idea of piecewise functions, because as we're going to notice in a second, a lot of the functions that we have learned in Precalc 11, Precalc 12.8, Precalc 12b, they're really nicely behaved. So we'll define that actually in just a moment. Infinite. So in this case, it's when you're kind of going along and then all of a sudden it's like, whoa, we had a bit of an issue there, and we're going up and up and up and up and up and up and up, and we could never even really describe how large those values were. And you can have the same thing kind of going on the other side. Those are going to be due to an infinite values, the discontinuity that occurs there. Oscillating. Yeah, this one, this one's a little bit funky. And so what ends up happening is you have this idea that you have this nice oscillating function, and it just kind of gets tighter and 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 tighter, and it gets kind of looser on the other side too, maybe. But if we were to zoom in here, you would see that this thing would just, it would have a period. Let me see if I can make one. So I'm going to switch over to graphing here. I can't remember one off the top of my head. I should have thought about it beforehand. But if I have sine of, and then I want my x values, I think if I did 1 over x, it might get it. All right, so if I were to zoom in here, this, as you can see out here, it's not really doing the whole wobbly thing much there. It's a very slow wobble. But if I were to zoom in here, that's weird. That's pretty cool, though. It basically just bumps up and down, up and down, up and down, up and down. And it does that as tightly wound in as you want as you go in further and further and further. If you were to plug a 0 into this function, you would see that it's going to break. It does divide by 0 problem there, so you can kind of see that there's going to be a discontinuity. But it's weird because you can almost imagine that this thing should give you a value because it's always being values in between +1 and -1. But where is it? We don't really know. So you don't know whether it's at +1 or -1 or 0 or whatever is going on when you go in there. At least, well, without doing anything too fancy there. So this would be an idea of something that oscillates and you can't really tell that it is going to go to a particular value. So it's a discontinuity relating to an oscillation. If you haven't seen oscillations before or talked about them a whole lot, you probably mentioned it in Precalc. But it's the idea of something that has a periodic motion. So back and forth, back and forth, back and forth, an oscillation. All right. So a function is continuous on an interval if it is continuous at every point on the interval. So sometimes we say that functions are continuous, and what we really mean is functions are continuous over their domain. So we don't expect functions to be continuous over parts where they're never existing anyway. For instance, if I mentioned a sideways parabola, so x is equal to y squared. Actually, I probably shouldn't do that because that's not really a function. So I'm going to actually just say y is equal to the square root of x, and that will be a function. So if I take a look at this particular function, that's continuous. I mean, it is. If I were to take that and draw it, I could start right at the origin, and I could go going backwards for me. So if I traced along it, I could keep going and not miss any points, not lift my pencil. So according to that weird definition, it definitely should be continuous. We don't expect it to be continuous when we have x values less than 0. I mean, we know that square roots of negative numbers don't work. So that would kind of be like our starting point. So there's an end point there. So we could still say that this function is continuous over its domain. And some people would even just say continuous period. And what they probably mean is that it's continuous over its domain. Now, if we have something where we have a part of a function, you want to describe that part of a function is continuous, then we talk about intervals. So as long as you can make an interval where you have some endpoints as part of your interval, and as long as it satisfies continuity everywhere on that interval, then it's okay to say that that function is continuous along the interval or on an interval in that particular case. Now, we have seen, and I'm going to actually take a little side note here, we have seen a lot of different functions in Precalc 11, 12a, and 12b. So whether that be, or before, linear functions, parabolas, absolute value functions, keep going here, exponential functions, logarithmic functions, trig functions, inverse trig functions. We would also have polynomial functions. We're going to see rational functions coming up. So you've seen a lot of different things. Now, the weird thing is each one of those can be traced without lifting your pencil for their domain pieces. So tan functions, for instance, they have a little bit of kind of an issue going on where you got this cool little squiggle And there are these asymptotes that occur before and afterwards, and we'll talk a little bit more about asymptotes when we get into rational functions. Wow, that's really messy. And then we would have that same sort of periodic motion going on, and then there's going to be something over here too. And the idea is you get that repetitive graph going on and on and on. Now, these parts right here and here are not a part of the domain. If you try to put an x value in to the tan function at pi over 2 or negative pi over 2, it's going to give you a domain error. Calculator won't be able to do it because there's no defined function, or the function doesn't work in a defined way at that value. So this thing is continuous over its domain, because if we go everywhere that's not in the domain, which is stuff like this and stuff like this, then each of those pieces can be drawn without lifting your pencil. So it's continuous over its domain. Oh, I had it switched over here. So tan function, talking about it, I'm going to be lazy and I'm not going to go back and fix that. Sorry for not switching that over. But that's kind of the idea there, is that I would have this thing, which is continuous over its domain. Now, almost every other function that we've seen, we can trace without lifting. So we're going to be really kind of cheating and say that all of those functions are continuous over their domain. All of them. Which means we're not left with very many examples that we need to cover, because every function that we have learned up until this point is continuous over their domain, except for these funky little piecewise functions. So funky little piecewise functions are basically just stitched together functions that are made up of pieces that we know about. So in this particular case, we have f of x is equal to, and then it's a parabola, upward facing parabola that goes through y is equal to minus 1. When you are on the left of 0. At 0, it is actually just a value of 3, if we look at the bottom one. And then when you're greater than 0, I probably could have changed the order of those two. When you're greater than 0, you're just a nice little linear function, slope of 1, also with a y-intercept of negative 1. So the question is this a continuous function? So as kind of like as I said, a little bit of a cheating thing that we'll be able to use all the time, basically, if we were on any one of these things individually, this is a parabola. Parabolas are going to be continuous over their domain. Continuous over their domain is linear. Constant value, continuous over its domain. So the only question is, well, this actually, it's a constant function. It would be continuous over its domain. Its domain is, in this case, 1 point. So it's a little bit questionable. But what we're going to do is say, this value, though, is sketchy, because what it does is it basically says, oh, but you were on that really nice, well-behaved function, but now you've switched. There's a chance that you could still be continuous when you switch, but there's a chance that you might not be continuous when you switch. So if we want to show that this function is continuous properly, there's 3 pieces to doing that. You might argue that it's 2 pieces, but the first piece is the left-handed and the right-handed limits have to be equal to each other, which means your overall limit is equal to each other. No, the overall limit exists and is equal to those right and left-handed limits. So, in this case, I'm going to say that the limit as x approaches 0 from the left. So I'm going to start on the left of my number line and work my way over. So these are values that are less than 0. So when I am doing the limit as x approaches 0 of f of x, that's the same thing as saying the limit as x approaches 0 from the left of x squared minus 1. Since this function is really well behaved, I could apply limit properties to this, but I can just plug in the 0, and that's a safe thing to do here. So that's going to be 0 squared minus 1, which gives me negative 1. So far, I found that the limit coming in from the left-hand side gives me a negative 1. If I take the same process, but coming from the right instead. We're doing a one-sided limit as we approach 0 from the right. When we come in from the right, I'm following this middle function instead. It's a linear function. So that's the one that's coming in from the right-hand side. So the first statement that I made, if I'm being really picky, I probably should put brackets around my first one where the limit is, because I don't really want it to be the limit of x squared minus 1 separately, even though it gives you the same answer. It's a little bit sloppy. So in this case, I'll have the limit of x minus 1. And again, this is a nice, well-behaved sort of function. So as we go along that line and we get close to the value of 0, you're going to be coming values like minus 1. So that is the same number from the left and from the right. Since those two things give you the same value, whether you're coming in from the left or from the right, I can say that the limit as x approaches 0 from the left of this function is equal to the limit as x approaches 0 from the right of the same function. Therefore, that means that this is also equal to the limit as x approaches 0 of f of x. So that exists and is the same number. Or if I wanted to, maybe this would be, I said it out loud this way. Might as well write it down. So that's equal to that. Therefore, so I'll do my little triple dot pyramid. The overall limit with no superscript, so no coming in from the left, no coming in from the right, of f of x does give me that same value of minus 1. So there it is. I have thing number 1, or thing number 1A and 1B. So you could, as I said, kind of think of this as 3 pieces that you need to make sure are all connected together and are correct. That's limit from the left, limit from the right, and then the actual function's value. In this case, though, you might just do it as the left and right, making an overall limit, or not in this case, but all the time. You can think of it like that if you want. So this is step number 1. I would say 2/3 of my students, when they get to assessments, they remember this. And they say, hey, look, I've shown that the limit is minus 1. That's true. And if the question asks, which it did on your first question on the last little assignment that I was asking you to do, if you were to answer the question there, you would say, oh, the limit as x approaches 0 is minus 1. It's correct. But I'm asking if this function is continuous, and there is another thing that has to be true for this function to be continuous. So the question is f at 0 equal to minus 1? And so how do we tell? Well, we look back at the function and we say something like, oh, well, we need to look at what happens when x is actually 0. When x is 0, we follow this rule, which says 3. So f of 0 is actually 3. So the limit as x approaches 0 of f of x is not equal to f is 0. Therefore, f of x is discontinuous at x is equal to 0, or it has a discontinuity at x is equal to 0. So is f of x a continuous function? No. F of x actually has a discontinuity on its domain. So it is defined at x is equal to 0. But it has a removable discontinuity that has occurred at x is equal to 0. I'm actually going to graph this thing for you just to show you. Oh, just going to show off how sloppy I am here. Let's see. Well, we have y is equal to x squared minus 1, and let's see if I can remember how to do the domain properly. So when the x values are less than 0, so that's fine. And then we'll have y is equal to x minus 1 when your x values are greater than 0. And then the weird thing, when you're actually at a value of 0, you are a value of 3. So if I take a look at this funky little thing, when you come in from the left and when you come in from the right, you do approach that same value. You're getting to minus 1. Desmos is pretty smart. If I actually click on the value of -1, it's going to tell me undefined, because I actually have not said that you are allowed to be equal to either the line or the parabola when you are actually at 0. This is a hole, and it's been removed. And the actual function, though, is kicking around up here. So it's it's a part of the domain, but it is not continuous. And so this is kind of the type of question that you'll usually be trying to answer when you're talking about things that are continuous or discontinuous. So yeah, I think that is probably good for now. I'm going to leave it at that, and I'm going to cover properties of continuous functions and maybe get into intermediate value theorem a little bit at the beginning of next week. And I will probably be posting an assignment soon to give you a little bit of practice with trying to figure out whether something is continuous at particular values of x for certain functions. So I hope you're doing well, and keep asking questions or dropping by. I've been really happy to give some feedback on some of the questions you have been working on. Don't get really concerned or bent out of shape whether you're getting things right or wrong, or whether I'm being really picky about notation or whatnot. I'm really just looking to give you feedback and keep you engaged, and so I've been really happy. Take care.